Alright, chemists, how are we going? Last video in our polymer series here. We need to kind of bring some... Oh, there's my last video done. We need to bring some of the properties, the different properties, words. We need to talk about some of the different properties of polymers. Anyway, I just thought this would round out the chapter based on past HSCs, and there are some black slides in here, which means it's probably not going to ask, so there's a bit of extension in there. But I thought I'd go through some stuff, okay? So the macroscopic properties, or the properties that we experience here at this scale of a polymer, they're a representation of the structures in the polymer chains, okay? The intermolecular forces between the chains, and the identity in the shape of the atoms bonded in the chain. So, intramolecular bonding, intermolecular bonding gives the properties of polymers. So important structural features such as crystallinity, branching, chain length, side groups, and cross-linking will dictate the property also of a polymer. Let's talk about crystallinity. The degree of crystallinity in a polymer dictates the properties such as rigidity, melting point, density, opacity, or how easy light transfers through it, and chemical resistance. Crystalline regions have high rigidity, high melting points, high density, low opacity, light doesn't travel through them as well, or low opacity, that means the opposite, doesn't it? Light travels through them very well, and high chemical resistance. So crystalline is the more ordered in the strands, okay? The more amorphous is the more kind of random, okay? So all polymers lie on a spectrum of crystallinity, and the amount of crystallinity can be controlled in the manufacturing process to achieve the desired product. So our perfect example there is high density polyethylene, low density polyethylene, okay? That's our perfect example. Okay, what else can... and we've talked about this earlier, is branching. So as we've seen in polyethylene, chains with little to no branching can pack together very tight. And the opposite, branch chains can't pack together very tight. And so dispersion forces come into play, low or high dispersion forces. Low branching, or very linear, results in a polymer that is more crystalline, dense, less transparent, and more rigid. The formation of branch polymers requires more energy to break covalent bonds. Okay. To create addition sites, and so they'll be more made in high heat and high pressure. I wondered where I was going there. Okay, so branching can affect those properties too, and we've seen that in HDPE and LDPE. Sorry about the brain fart there. Chain length. Okay. So how long these polymers chains? We haven't talked about that. So when polymers are made, a deviation in chain length is the result. You get like a curve, a distribution of them. You get really short ones, and most of them have kind of like a medium range, and you get a few going really, really long. So the conditions of the reaction can be altered so that you can change the average. You can shift the curve up or shift the curve down, okay? If you want more longer chain, the longer chain lengths are smaller the variation in lengths, the higher the melting point and the harder the polymer, because you're getting more dispersion forces between, and you're getting less molecules and longer molecules. So the average length affects the flow of the softened polymer. So when you heat it, and it's kind of liquidous or flowing, so the average length affects that flow, which will in turn affect the manufacturing process, because you need heat. So longer chains will result in more viscous flow, so thicker like honey, while shorter chains will be thin and flow easily. So shorter average chain polymers will therefore not mold very well, as they run off the mold before drying. Okay. Side groups. So, we can compare PVC to polyethylene. PVC, remember, you're getting these benzene rings on the side. Remember, it was every second one, okay? The more side groups, and the larger the side group, the less flexible and the more rigid it is. So one of the properties of oh, this is not PVC, this is polystyrene. One of the properties of polystyrene is that it's very rigid because of those side groups, the benzene rings. The one thing that we can do is we can alter which side these side groups are. And this is called the tactility or tacticity. Okay, and it's the spacing of the side groups will also affect the properties of the polymer. So you can have them all over one side, you can have them alternating, or you can have them random, and it gives different properties to the same type of polymer, slightly different. Okay, the isotactic, and so the one where they're all over one side, and the one where they're regular, alternate chains will line up really well with each other. They'll slot in or they'll be on the opposite side. So they can move really close to each other. So they have higher melting points and stronger chemical resistance. But this random one, it doesn't line up very well with another random one. So it has lower melting points and you can get more chemicals going in between there. There's some more detail about each of them there. I don't really think that they're going to go into that too much. It was part of the old HSC. It hasn't mentioned it, but it's there if you want to go a little bit deeper. Okay, another property of plastics, well, it might not be asked about, it could be. It's for everyone's knowledgeability words. Everyone should know it. So biodegradable plastics are designed to break down into smaller pieces readily. Okay, most of these are just the original plastic, like polyethylene. They've been copolymerized with a rubber polymer or a starch. Okay, and that basically because that more natural polymer will react with oxygen. It'll break the polymer chains down. Okay, the idea that something is biodegradable if it breaks down into the smaller pieces, I'm calling it naive. Okay, what you're just going to end up with is smaller pieces of plastic. Okay, instead of large bits of plastic, you've now got smaller bits of plastic. Different problems. Okay, smaller bits of plastics are not being consumed by decomposing organisms. There are some weird examples, but in general, no. They're sticking out there in the ecosystem as just tinier bits of plastic. Okay, they're not being recycled. We now have microplastics, okay, in our ecosystem. Biodegradable plastics in general pose more severe threats to ecosystem than large pieces of plastic. So be careful. Biodegradable and compostable plastics, be very, very skeptical about. Okay, do you want your plastic as one big piece of bag, okay, where it can do harm in the environment to very larger animals, or do you want it in millions of smaller bits that can kill millions of smaller animals? Let's not have it at all, okay? So be very skeptical about biodegradability in plastics. There are compostable plastics, still may have the same problem, okay? It is not a solution at all. Reducing and recycling, or just reducing, is the best, okay? If you want some more detail, there's a link to a good conversation article. Okay, we talked about cross-linking, so I won't talk about that too much, but there's some new diagrams there. Stability. Okay, this goes back to that biodegradability as well. Stability is basically how long the polymer lasts, okay? And it depends on the bond's presence. It depends on the bonds in there, okay? If you have more polar bonds, like PVC has that carbon to chlorine bond in there, it has lower bond energy, and UV light can break these bonds. And if it's breaking those bonds, it's causing radicals, and it's causing these long chains to break, and also for the plastic to break on the larger scale. So over time, you'll see that some plastics go brittle and break when exposed to light, in UV light, or go yellow, and they break down into smaller pieces. That's what's happening. These bonds are breaking. Okay, so one thing that's signed is PET bottles have a use-by date on them for water. The water doesn't break down. The water doesn't have a use-by date. But the plastic breaks down and starts entering the water and dissolving in it. And also you lose the integrity of the bottle. That's the use by date on the bottle. So you also get reactions with oxygen causing breakdown of the polymer chains. Okay, so breakdown at the molecular level is reactions by UV light breaking bonds or oxygens reacting and breaking these chains. What happens are there are chemicals, different chemicals that we call in general stabilizers to extend the life of these plastics if we want them. Usually what they do is they preferentially absorb UV light before they get to the chains, and they change it into heat. Okay, ones that prevent against oxygen are antioxidants, so they preferentially react with oxygen. Okay, there's other things called plasticizers. I really think that's extension material. Let's do a couple of quick questions before we finish the chapter. Here's one from 2013. Look at this cup. Renewable creations made from plants. What is the structure of the polymer most likely to be used in the manufacture of the cup shown? If it's made from plants, that's polyethylene. That's not made from plants. That's polystyrene. That's not made from plants. That's polyvinyl chloride. That's not made from plants. Oh, look at these chains of saccharides or sugars. Tick. That's made from plants. Okay. A polymer shows the following structure. Oh, every second one is a methyl branch. That's opposite sides though. Which of the following represents the monomer from which this polymer can be produced, not pictured. Okay, so it hasn't got the functional groups in the chain, so it's not a condensation reaction. So it must have a double or triple bond in there first. Get rid of our diol. Okay, our diols, remember, will react with carboxylic acids too, so it must be a copolymer then. Okay, look at this. Okay, the reaction's going to happen between there. Look at this. This has got an ethyl branch coming off it. Do we have ethyl branches coming off here? No, we have methyl branches. Look at this. This one here has a methyl branch off the second one. This one up here has a methyl branch off every second one. Good. Now let's check A. This one has a methyl branch off both of them. Does this one have a methyl branch coming off all of them? No, it's not that monomer. So it's D, which is our propene. So that's polypropene. Which row of the table correctly matches the polymer with its structural feature and property? 2018, question 11. Okay. Polyvinyl chloride, okay, has a chlorine side group and that makes it relatively rigid. Okay, let's see if there's a better one. LDPE, low density, remember the really branchy one, they can't fit together. It has tightly packed molecules. Nah. Get rid of B. High density polyethylene has very straight chain molecules. Get rid of C because it says branch chains. Polystyrene has large side chains. Yep, good. It has the benzene rings. That means it's flexible. No, the opposite. That means it's rigid. Alright. So notice there I kind of had one, but I mean, properties like flexibility and rigid is all relative compared to other ones, okay? I knew that polystyrene was not flexible, no. So it must be A for that one. Okay, there's what you should know. That's what you should be able to do. I think we're finished the chapter on polymers. Hopefully that's helped out. Hopefully the past HSC questions are kind of giving you an idea of what they could ask. Thanks for your time.